So which one is bigger would mean which one gets away from its mean more. So this one is definitely a bigger standard deviation, right? This one has more right on the mean. It's going to get away from its mean less often. So what we did earlier was we discovered this. If that guy is sigma, this guy's standard deviation is going to be, and here's the notation for this. What are all these? What's this little point here mean? This is an individual person. What is that little point? The average of 15. So a sample mean, right? So this would be the standard deviation for the sample means. Oh, shit. In fact, the really cool thing, I want you guys to realize something before we go any further. Just whatever data I have in here. When you do 1var stats, what does it say for sigma? Sigma x. So we normally don't write sigma x. But do you see what it would mean? Sigma for individual values. So this is going to be sigma for x bars. That's going to be the standard deviation of the means. How spread out are the group's averages from each other? Okay, I love you guys. So look what this is boiling down to. I know right now you're like, I didn't know I could hate this guy more. I didn't know I could hate this class more. But please, hopefully some of this is making sense. You are worried about what you are going to have to do. Is this correct? If I were you, I'd be sitting there going, am I supposed to make alternate universe Minnesota? The shit's that look like, Jeff? No, you don't. No. The only thing you're going to have to do is change the standard deviation. If I say we take a group of 30 things, what's the probability that its sample mean is greater than 7? I cannot use this because this is for individuals. I have to use this because that's the one that works for groups. All the work we've done would stay the same. The only thing I'm going to do is I'm not going to divide x minus mu divided by this. I'm going to divide it by this. Wow, they're really early. All right. I didn't want to be out in the rain. It's too bad. Such a caring guy. And the really neat thing is, once you get greater than 30, this is where the real magic happens. Once you get samples bigger than 30, let me ask you this before I even say what I'm about to say. If I just took a sample of 30 people, is there any reason their distribution should look a certain way? Just take random 30 people and get their ages. Does it have to be normal? Does it have to be uniform? Does it have to be anything? It could be whatever the shit, right? But, so it's not what I'm about to say. If I take samples greater than 30 and plot every single sample mean, the result is normally enough. Or approximately normal, to be more precise. That is huge. Why? If I know I have a normal curve, do I have a sheet of answers? Yeah. So, yeah, I want to know, when can I use this? This is all answers. When can I use it? Well, now we know. In this situation, if n is greater than 30, I know I've got a normal distribution. Then I can use this chart. All right, so let's do one concrete problem before we leave, so you're not all kind of like in limbo about what the shit is up. All right. So here comes a concrete problem. So let's say given a normal distribution with the mean of 98 and the standard deviation of 11.2. I like it. If we pick one data point, find the probability that it is less than, what you got, Chuck? Less than 92, right? Now this might seem, I don't care, it's not trying to be evil. This is old. This is old news. Nothing new here. I don't have to change anything because this standard deviation is the standard deviation for individuals. And how many am I picking? One. So that standard deviation works for this guy. So this is like we've been doing for a while now. Draw the picture. Put the mean in there. Put 92. Make it a z-score, right? Let's see. Make it so everybody can see. Keep toning. All right. So if I make this into a z-score, this is what we were just doing, right? 92 minus 98 divided by 11.2. All is good. All is normal. Something like 0.53 or something. 54? Negative, yeah. Well, I missed the big things. Good job, Joe. Negative because it's down there. So, all right. I'm going a little bit quickly because we've done a ton of these. But I really want to show you, I love doing this kind of problem. The first part is old stuff. So I know this is negative 0.54, so when you look that up, you'll get the answer. So if you look up negative 0.54 on the chart, do it again. 2946. Okay, now, here comes the new shit. Here comes the new shit. You can do it, Jeff. Your spacing is weird. There you go, Mike. If you take a sample of, what you got? 16 data points. What's the probability that their mean is less than 92? First question is, that 30 number is going to become huge. But that's only required if I have no idea what it looked like to begin with. Was this normal already? Yeah. So how big do I need of a sample to make it normal? It's already normal, so I don't have to have 30. If I did not say normal, n would have to be greater than 30 or I couldn't do shit. Because then how could I know to use a z-score chart if it's not normal? This one said it's normal. I don't care how big the sample is. It's normal already. So the big thing that changes, the only thing that changes, the mean is still 98, 92 is still there. I still shade that in. I took a sample and I'm asking about the sample mean. Therefore, this will not apply. This can't possibly have shit to do with that because this is for individuals. And I need to know the spread of groups of 16. How spread out are they? This picture is of individuals. That picture is for samples of 16. So I can't quite do my z-score yet. I just have to get the right standard deviation first. So it's going to be what I call the old standard deviation, but the one for individuals divided by square root of what? 16, because that's how big the sample was I took. Oh, 2.8? Yeah. So watch. I did everything we just did here, didn't I? Except for one extra thing. I changed the standard deviation. Now I do everything. So now I still do z-score. It's my data point minus the mean divided by the appropriate spread, which is 2.8. So conceptually, it took me a long ass time. You could say because it's a weird concept, or you could say because I suck at making something efficiently explained. Either way, you want to say it. But nuts and bolts wise, that's the only thing that changes. You just have to remember When? When does that come into play? So let's see, what are you guys getting here? Negative, who is it?
2.14.
2.14? Okay, all right. And then if you look that up, what do you get? Oh, 162? You guys getting that same thing? Oh, 162? Yeah? So real quick, when I take a sample, the picture gets skinnier. You know, you don't have to draw the picture differently, but it does. It gets skinnier because it should be less likely to get a 16 down here. It should be more likely to get them in the middle somewhere. So doesn't it make sense that there's almost 30% in the original picture here, but if I get it skinnier, there should be less out here, 0.0162. There's less out there. More of it goes to the middle. So we just got into that a little bit. So next time we'll definitely do a lot more. This is called central limit theorem, by the way. CLT. I call it chicken, lettuce, tomato, but you don't have to. So don't freak out about that yet. We'll do more of it next time.